Welcome back to lecture 2 of the module Electrochemistry. So we'll continue the topic. In the last lecture, we discussed standard electrode potentials. So where we discussed the calculation of the cell potential as the difference between the half cell potentials of the cathode and the anode. So let's take an example problem. So they have given us a skeleton equation. First, they're asking us to write a balanced equation and then calculate the E of the cell. So you already know the method to do that. So make sure to split it into two halves, balance the equation using the method, and try to write down the equation. So this is the balanced equation that you'll be left with. Now, this is the overall balanced equation. Now, how do you calculate the half cell values of each of these? So we can use the table at the end of the textbook in Appendix D. You will find the half cell values of different reactions. So for example, you can note that the manganese value is plus 1.23 and bromium value, so bromium value is around 1.5. So you have to know that the difference here is you are calculating two separate values. One is manganese, the other is bromium. So when you use the table, you will find the following values. So for notice that here oxidation is going to undergo for manganese. So manganese is the molecule that is undergoing oxidation, and bromine is the molecule that's undergoing reduction. So therefore, when we say that here, what is the E of the cell? So E of the cathode minus E of the anode. So the cathode here is the bromine value, and the oxidation is for the manganese value. So for bromine, it's 1.07 minus the anode manganese is 1.51, so which gives you a value of negative 0.44 volts. So the negative sign here implies that the cell reaction is not spontaneous reaction. So what are these standard values? How do you get them? So let's start with the standard hydrogen electrode. So half cell potentials are generally measured relative to a standard reference half cell. That standard reference half cell is the zero value, which we generally use to represent for hydrogen. So the standard hydrogen electrode has a standard electric potential of 0. So it's not plus, it's not minus, it's just 0. This standard value consists of a platinum electrode with hydrogen gas at 1 atmosphere bubbling through it, and the platinum electrode is immersed in a 1M strong acid. So when you have 2H plus 2 electrons gives you H2, the reference value there is going to be 0. Now let's take a simple example of how to determine the unknown value of a half cell. So how would you calculate for a standard electrode? Let's say, for example, we are trying to calculate the half cell potential of zinc. So the oxidation half will use zinc and the reduction half will use water, and the overall cell reaction results in this reaction right here. Now when you calculate the value, let's say for example you have a problem here. A voltaic cell houses the reaction between aqueous bromine and zinc metal. So you have bromine plus zinc gives you Zn2 plus 2Br minus. So the total cell potential is 1.83, and they are asking you to calculate the cell potential of bromine while the zinc potential is given as negative 0.76. So first things first to remember here is to take into consideration the idea of which one is oxidation, which one is reduction. So zinc here is losing electrons and bromine here is gaining electrons. So when bromine gains electrons here, we can say here that we have bromine Br2 becoming Br minus. So when you balance the equation, that gives you bromine becomes 2Br minus, and because there is 2 electrons deficiency on the left side, so we can add those 2 electrons here, gives you 2Br minus. So this is the balanced equation for bromine. Now let's try to balance the equation for the other half of the reaction, which is the zinc. So you have zinc Zn becoming Zn2 plus. So for zinc to become Z, so notice that it's already balanced, that there is 1 of zinc on both sides. Now notice that it has 2 plus here, so and there is 0 here. So add 2 electrons to the right side, so you get Zn becomes Zn2 plus 2 electrons. So resulting in this value right here. So now we have two reactions. So this part is the reduction and this part is the oxidation. So the oxidation is always the anode and reduction is always the cathode. So E of the cell becomes E of reduction, so which is the cathode, minus E of oxidation, which is the anode. So the total cell value is given as 1.83. So they have given the total cell value as 1.83 and the zinc value as 0.76. So the reduction is occurring for bromine. So we can write that this value here is for bromine minus E value for zinc. So this is the cell reaction, cell potential formula. So the cell value is 1.83 equals E of bromine. We do not know that value, so let's keep it to the side. Minus of E of zinc is negative 0.76. So E of bromine plus 0.76 becomes equal to 1.83 and E of bromine is 1.83 minus 0.76, so which gives you a final value of 1.07 volts. So this is the E value for bromine. So this is how you can use the formula here to calculate the values. So how do you compare the cell potential values? So standard electrode potentials generally refer to the half reaction as a reduction. Now the E values therefore reflect the ability of the reactant to act as an oxidizing agent. So the more positive the E value, the more readily the reactant will act as an oxidizing agent. The more negative the E value, the more readily the product will act as the reducing agent. So when you notice the values here, on one end of the spectrum you see lithium, which is a really strong reducing agent. So which means here it undergoes reduction faster. So therefore as you go down towards lithium, so the more negative the value, the stronger the reducing agent, the more positive the value. On the other end of the spectrum you have fluorine, which is a really strong oxidizing agent, which means it readily undergoes reduction. So therefore it has a really big positive value. So the more positive the value, the more the oxidizing ability that it has. So the more the strength of the oxidizing agent here increases and the strength of the reducing agent, reduction capacity decreases. So next let's talk about writing spontaneous redox reactions. So we know that each half reaction contains both a reducing agent and an oxidizing agent. So the stronger the oxidizing and reducing agents react spontaneously to form the weaker ones. So a spontaneous redox reaction generally occurs. So the spontaneous redox reaction means that the cell potential must be greater than 0. So will occur between an oxidizing agent and any reducing agent that lies below its EMF series. Remember here that the oxidizing agent must have a higher value than the reducing agent. So only then will this reaction properly occur. So that is one less than one that has a less positive value for E prime. So the oxidizing agent is the reactant for the half reaction with more positive E value, and the reducing agent is the one that has a lies below the oxidizing agent's value. So let's say you are using half reactions, so there we are trying to write spontaneous redox reaction. So let's take into consideration these two reactions right here. So you have Sn2 plus 2E minus gives you Sn, so which is tin. So the E value for tin is negative 0.14 and Ag2 plus E minus gives you Ags. E of silver is 0.80. Now we do not know which one is oxidation, which one is reduction. First one is to compare the values. So first thing to remember is to always take the values and flip the value that is positive. So take the reaction that has the smaller E value and flip that reaction. So when you flip this reaction right here, so that becomes Sn gives Sn2 plus 2E minus. And so this, the flipped one, notice here that tin here is losing electrons, so this becomes oxidation. So the one that has the lesser value will always be the one that undergoes oxidation, and the one that has a higher value, so the Ag plus E minus becomes Ag. So this is the reduction reaction. So the oxidation is the anode, the reduction is the cathode. So the E of the cell becomes E of cathode minus the E of anode. So the E of cathode, the value is already given here. So the E of cathode, the cathode that we have decided here is silver. So E of silver minus E of tin. So the cathode value is 0.80 minus of minus 0.14. So which becomes 0.94 volts. So this is the value of how to calculate the actual values. Now always remember, whenever you calculate the values, make sure to also write the overall balanced equation, just so that we have an idea of how many electrons are being transferred from one reaction to the other reaction. So pause the video right here. Here they have given us 3 reactions and they are asking you to calculate E of cell for 2 each of these combinations. So first do 1 and 2, calculate the E cell value. The same thing, do 2 and 3, and then do 3 and 1. So using the principle that we just did right now, use those principles and try to calculate E cell for each of these combinations and try to solve this problem. So pause the video right here and try to solve this problem. So now let's continue our topic, the activity series of metals. So metals that are generally, that can displace hydrogen from acid are the stronger reducing agents than hydrogen. So whenever you have, let's say for example, 2H plus 2 electrons, it gives you H2, and you have iron which becomes Fe2 plus 2 electrons. So iron here is considered to be a strong reducing agent. The main reason is because it can displace electrons from hydrogen. Now the combined product results in the formation of a hydrogen gas, and always the one that is negative undergoes oxidation, the one that is more positive undergoes reduction. So therefore gives you the E cell value of 0.44 volts. So the lower the metal is in the list of half cell potentials, the more negative its half cell value, the stronger it is as a reducing agent. So the more negative its value, the stronger the metal is a reducing agent. So the more negative the E of the metal, the more positive its E cell value, and the reduction of H plus, the more active a metal it is. So metals that cannot displace hydrogen from acids are generally weaker reducing agents. For example, silver is a metal that generally cannot displace hydrogen from the acid. So the higher the metal is in the list of half cell potentials, the more positive its half cell value and weaker it is as a reducing agent. So the more positive the half cell value of a metal, the less positive its E cell value for reduction of H plus, and therefore the less active the metal is. So metals that cannot displace completely, that can displace H2 from water, are metals whose half reactions lie below that of H2O. So more commonly you will have to look for values anything that are below H2O. So only those are the ones that can have a really good value for the potential. So next, let's go to the next topic, free energy and electrical work. So for a spontaneous redox reaction, we know that delta G is less than 0 and E of the cell is greater than 0. So we can use both of these and write a combined equation for the free energy. Delta G can be written as negative NF E of the cell So here E here is not the standard electrode potential, but rather the cell potential. Now when you want the standard and standard free energy, then that gives you minus NFE of the cell. Now, under standard conditions, we can also consider E of the cell here becomes delta G, which can also be written as minus RT ln K over NF. So when negative go on the other side, so you end up with negative gone, so you'll end up with RT by NF ln K. So we know that delta G prime is minus RT ln K. So this is the principle that we use in this equation. So we get from this we can get directly the E of the standard electrode potential of the cell, which can be calculated as RT by NF ln K. So what is this F here that we have mentioned a lot? So F here is called as the Faraday's constant. So or the Faraday constant. So this Faraday constant is equal to 9.65 times 10 to the power 4. So joule per mole of electrons. So N here represents the number of moles of electrons being transferred. So N here represents the number of moles of electrons, and F here represents the Faraday's constant, and E here representing the cell potential. So now we have all these values combined, which gives you a sense of how the reaction generally unfolds when you compare the values of delta G, K, and the cell potential. If delta G is less than 0, K value will be greater than 1, and the cell potential is greater than 0. So this here is a spontaneous redox reaction. So this is a spontaneous redox reaction. If the delta G is equal to 0 and K is also equal to 1, then E of the cell is generally equal to 0, which results in a reaction that is at equilibrium. And if delta G is greater than 0, K is less than 1, and E of cell is less than 0, so we can say that that reaction is a non-spontaneous reaction. So this is the way with which we can compare between the reaction parameters at the standard state. So let's take an example. So we have lead can displace silver from solution, and silver occurs in trace amounts in some ores of lead. So you have lead plus silver gives you Pb2 plus 2Ag. So as a consequence, silver is a valuable byproduct in the industrial extraction of lead from its ore. So they're asking you to calculate K and delta G at 298.15 for this reaction right here. So now let's take the example right here. So they have given us a temperature of 298.15, and they're asking us for this particular reaction right here. So first thing to note is to write down the values for the potentials. So from the end of the table, so these values will be given in the examination, so you don't need to actually write down that. So for now I'm going to write down these values. So for silver, so E for silver is 0.80 volts, and Pb2 plus so E of lead is negative 0.13 volts. So how do you calculate the reaction? First thing, to note down which one is the least values of the electrodes, the cell potential. So the second one here, so flip the reaction. So that becomes Pb becomes Pb2 plus 2 electrons, and Ag plus an electron gives you Ag. Now notice that there are 2 electrons here, there's only 1 electron here, so multiply this with 2. So that gives you a total of 2 electrons in the entire full reaction. So 2 electrons gone, so which gives you Pb plus 2Ag plus gives you Pb2 plus 2Ag. Now notice here the number of moles of electrons is 2. So 2 moles of electrons. And we have to calculate the delta G value. So to calculate the delta G value, we need the cell potential value. So the cell potential value can be calculated as E of silver. So now this is oxidation and this is reduction. So oxidation is the anode and reduction is the cathode. So the one that undergoes, so E of the cathode here is silver minus E of lead. So which can be calculated as, so E of silver here is 0.80 minus E of lead is negative 0.13. So which when calculated gives you a value of 0.93 volts. So this is the standard cell potential of 0.93 volts. Now first things first is to notice the reaction. The cell potential is equal to RT by NF ln K. So this is one reaction. The other reaction is delta G prime equals negative NF E cell potential. So first they're asking us to calculate delta G prime. So let's calculate delta G prime. So minus N here is 2 moles times EF here is 9.65 times 10 to the power of 4 joule per volt mole of electrons. Now times E of the cell. So E of the cell is 0.93. So which when finally calculated will give you a value of 0.93. So let's use a calculator. So you have 2 times 9.65 times, so 10 to the power of 4 times 0.93. So which when calculated gives you 179490 joules. So which when converted into the scientific form so which will give you around 180 kilojoule per mole. So delta G is negative 180 kilojoule per mole. So we conclude that from delta G being less than 0, so that this is a spontaneous reaction. Next we'll calculate the K value. So from this we can write that ln K equals E of the cell times NF over RT. So E of the cell times NF, which is basically equal to delta G, so which value is minus 180. So write down the value right here. So 0.93 times 2 times 9.65 times 10 to the power of 4 by R here is 8.314 times the temperature given is 298.15. So let's take in this value right here. So divided by 8.314 times 298.15. So which when calculated gives you an ln K value of 72.409, but we know that K value can be written as, so when ln goes this side, so it becomes e to the power 72.409. So let's calculate that value. So you have e to the power, so that gives you a value of 2.799 times 10 to the power of 31. So that is the value for K. So this is the K value for the reaction. So this is how you can solve the problems that involve free energy and electrical work. So next, let's talk about cell potential and concentration. So for that, we generally use the Nernst equation. So Nernst equation represents the cell potential under non-standard conditions. So when you have the standard cell potential and when you have a concentration cell potential, we are basically taking this concentration cell potential as the difference between the standard cell potential and the non-standard conditions. So the Nernst equation represents the non-standard cell potential. So which can be calculated as E of the cell equals the standard cell potential minus RT by NF ln Q, where Q here is the reaction quotient. So based on the conditions here, we can calculate the cell potential. Now, if this value Q is less than K, so if Q is less than 1, so which means that the ln value, ln of Q, which results in the reactant concentration. So if Q is less than 1, it basically says that the reactant concentration is less than the product concentration. So reactant concentration is greater than the product concentration. I'm sorry, Q is product by reactant. So reactant is greater than product. So which results in ln Q being less than 0. So if ln Q is less than 0, so then the total value becomes negative. So which results in E of the cell being greater than the standard cell potential. If Q is equal to 1, then the reactant concentration is equal to the product concentration. So which means that ln Q will be equal to 0. So which results in the cell potential being equal to the standard cell potential. And the final condition, so which is when Q is greater than 1, which means the reactant concentration is less than the product concentration. Then that leads to ln Q value being greater than 0. So which means that here the cell potential will be less than the standard cell potential. So these are the three conditions we can use to understand this. Now to simplify this equation, the Nernst equation, we write down the constants and the temperature and write down the simpler equation, which results in a log value rather than ln value. So which can be written as E of the cell equals the standard cell potential minus 0.0592 by N log Q. Again, remember that both equations are correct, but only the fact is that we are only changing it to make sure that we can write down the equation in a comfortable form. So which results in the cell potential minus 0.0592 by N log Q. So where N here represents the number of moles of electrons in the redox reaction that are being transferred from the oxidation half reaction to the reduction half reaction. So let's start a problem. So you have, in a test of new reference electrode, a chemist constructs a voltaic cell consisting of a zinc half cell and a hydrogen half cell under the following conditions. So the zinc concentration is 0.010 m, the H plus concentration is 2.5 m, and the partial pressure of hydrogen is 0.30 atmosphere. So they're asking us to calculate E of the cell at 298.15 Kelvin. So now let's take into consideration both zinc and hydrogen. So you already know the equation for hydrogen. Hydrogen is 2H plus 2 electrons gives you H2. And the cell potential, the standard cell potential for hydrogen is 0 volts. For zinc, so which is Zn2 plus 2 electrons becomes Zn. So the standard cell potential is negative 0.76 volts. So these values are generally given in the final part of the table. Now notice the one that is smaller here is the zinc value, so which we'll have to reverse. So the reaction becomes zinc becomes Zn2 plus 2 electrons, and 2H plus 2 electrons becomes H2. Now notice that both of them are balanced now. The final reaction has a N value of 2 moles of electrons. So the final reaction becomes zinc plus 2H plus gives you Zn2 plus H2. So zinc here is solid, 2H plus is aqueous, Zn2 plus is aqueous, and H2 is a gas. Now from this we can write the cell potential, the standard cell potential. So for this, the E value for zinc is minus 0.76 volts, and E for hydrogen is 0 volts. Now E of the cell is anode here, which is the oxidation. So this is the cathode, which undergoes reduction. So we are talking about E of the cathode. The cathode is hydrogen minus the E of the anode. Anode is the zinc. So it becomes 0 minus of minus 0.76. So the cell potential is 0.76 volts. So the cell potential, the standard cell potential is 0.76 volts. But we are trying to calculate the actual cell potential. So where we will need the Q value. Now they have not given us, so the ones that we do have. So let's take a look at the Q equation from this equation right here. So for this equation, we have everything written in this form right here. So the aqueous zinc, so from this equation right here. So let's copy this equation from here. So this is the equation that we have. So the Q value can be written as the concentration of hydrogen times the concentration of Zn2 plus divided by the concentration of H plus. Notice here that the H plus square, sorry. So notice here the zinc is a solid, so which is not considered under the reaction quotient formula. Now we have all the reactions now. So notice here, they have given us the concentration of Zn2 plus, which is 0.010 m, the concentration of H plus, which is 2.5 m. So the concentration of Zn2 plus is 0.020 m, so 0.010 m, and the concentration of H plus is 2.5 m. So, but they have given us the pressure of hydrogen, which is 2.5 atmosphere. So 0.30 atmosphere, but we do not know the concentration of H2. So the concentration of H2 is the number of moles by volume. So, but we do know that pressure times volume equals nRT. So when you want N over V, just push RT to this side. So you get N over V equals P by RT. So the pressure here is 0.30 atmosphere. So 1 atmosphere is 101. So we can directly use the atmosphere value itself. And the R value in atmosphere is 0.0821 atmosphere liter per mole Kelvin times the temperature is 298.15 Kelvin at room temperature. Now again, so from this, when you calculate the final value, so that gives you the concentration of H2. So the concentration of H2 becomes 1.2 times 10 to the power negative 2 m, so which is basically 0.012 m. So this is the concentration of H2. From this we can directly calculate the Q value right here. So the Q value, which is the concentration of H2 times the concentration of Zn2 plus over the concentration of H plus square. So the concentration of H2 is 0.012 m times the concentration of Zn2 plus is 0.010 m by the concentration of H plus is 2.5 square. So let's calculate the value. So 0.012 times 0.01 divided by 2.5 square. So that gives you a value of 0.4000192. So which is basically 1.92 times 10 to the power negative 5. So now we have everything that we need. So let's try and make sure that we can convert this into a much more easier understanding of a problem. So we have the Q value now. So we know the E of the cell is E of the cell minus E cell. Sorry, the non-standard, so non-cell potential is the standard potential minus RT by NF. So which we've written as 0.0592 by N log Q. So E of the cell we calculated is 0.76 volts minus 0.0592 by N. So the N value that we calculated from the reaction is 2 moles. So 2 moles by 2 times log of 1.92 times 10 to the power negative 5. So 0.0 minus of, so 0.0592 divided by 2 times log of 0.000192. So which when calculated gives you the final answer. So which is 0.8996. So which can be written as 0.9 volts. So the non-standard potential is 0.9 volts. So this is the potential of the cell. So if the E value is greater than E value is greater than the standard potential, we can say that Q is less than 1. If E is equal to E, then it is equal to 1. If E is less than the standard potential, it's greater than 1. And if it is 0, then Q value is equal to K, which means that this is at equilibrium.